I open it for questions. I guess we will roll questions for Ron to the next part of the program, which is about 15 minutes allocated for discussions related to the atmosphere and precipitation. So the good news is after that there will be the break, so be energized, ask the right questions if you have, otherwise we will ask the organizers what to do. Wait, don't rush. Any questions for Ron? All right, Ron, thanks so much. Appreciate it. Are there any general discussions related to two topics that Ron and Roy presented? Yes, Howard.
Well, I think Roy has kind of given us a vision of where very recent developments in high-resolution atmospheric modeling have really been quite transformative. And coming to Canada, the biggest problem that we have in hydrology is not knowing our precipitation. I was really impressed when I saw his early results of snowfall over the US Rockies. It's worthwhile pointing out that Yangping Li here has been working very closely with Roy, and we're just closing the Changing Cold Regions Network, and the 4-kilometer modeling that she's been doing in conjunction with Roy has been quite definitive in giving us really important insights, particularly into amount of precipitation, but also the downstream movement. So maybe the question for Roy is, where are we going in the next 40 years? It seems to me that there's going to be much more close coupling between atmospheric and hydrological modeling to look at these really complex issues of mountain hydrology. We have some interesting issues with Yangping's simulations because they're really terrific in most respects, but they have small biases, like small temperature biases and some precipitation biases. Actually, those biases, although they're very small, are really sensitive in terms of the hydrological modeling. I think Sarush made a comment about are we going to 25 centimeter resolution or something, but maybe Roy, you could give us your view as to this is an exciting new phase, but where is it going in the medium term to resolve these biases?
Well, it's a great question. I just 2 days ago, I wrote a strategic plan for our research moving forward in the future, so I've been thinking about this. I showed you MCSs, and we talked about snowfall, snowpack, and we realized there are biases, so there's work to be done with the land surface models. I think the albedo is not quite there yet in terms of snow albedo and how that feeds back on the temperature. So there's still a lot of work to be done. We talked about this at the in-arch meeting about blowing snow. How do we, even though we're running at 4 kilometers, the blowing snow really needs 100-meter or 10-meter scales according to John. And I'm not going there, John, but we can maybe parameterize it. And so there's a whole area, I think, of work to think about how do we parameterize blowing snow in these grid cells. I think the work that we've done is starting to show that for most mountain ranges that are not too complicated, most of them in the U.S., 4 kilometers seems to be adequate to capture the vertical motion that drives the snowfall, drives the snowpack. However, there are specific regions with very sharp peaks and very steep topography where we underestimate. So in some cases, we need to go down to 1 kilometer. And in fact, in the Vancouver Olympics, the Canadian Met Center ran 1 kilometer nested model, and it did fantastic. They got the downslope, upslope flows. So if you want to capture those katabatic flows, you need to go down to 1 kilometer. I showed you MCSs. Those are organized, large-scale systems, and they produce a lot of precipitation. But we're having problems in the southeast United States, just ordinary convection. So 4 kilometers doesn't necessarily resolve ordinary convection. And there's entrainment in the clouds that I haven't talked about. That's another issue. So if we go down to 1 kilometer, we actually do better with the southeast convection. That's important part of the water cycle. So there are many aspects of this. The UK Met Office is running its global forecast models at convective resolving as well, not necessarily over the whole globe, but over regions like the UK and Singapore and other areas. And they're finding some challenges even at these scales. So we've started a workshop. We had one in 2016, and there's going to be another one in Boulder in 2018. In September, anyone's invited to participate, but this whole community of convective scale climate modeling is coming together. It's just exploding. If you look at the number of papers, it's going up exponentially. So this whole area is growing, and I think there's a lot of work to be done. Then coupling it to hydrology, I think, is really a challenge that really hasn't been done yet. I've got 10 hydrologists in my group at NCAR, but none of them want to, only a few of them have actually taken the challenge to run the hydrology model with the CONUS 4 kilometers. And I think that's another area that's ripe for investigation. I think Eric showed us a wonderful global data set at the 4 kilometers or 12 kilometer scales, the same type of future issues. And I think we could use data sets like the ones that Eric has produced to actually run our models. One last comment, sorry for the long answer to that question, is we're moving towards other regions of the globe. So China, India, and as part of GWEX, we're looking at water for food baskets. So a lot of discussion this morning and this afternoon about water nexus, water-food nexus. I've been taking notes, so I'd love to talk to you. We're going to have a GWEX open science meeting here in Kenmore in May, and we're going to have a town hall on water for food baskets. It's a grand challenge in the GWEX program. So all of these things are coming together. I think it's at a very exciting time period.
Yeah, Roy, just in response to the downscaling, we don't have to go to 10, but hundreds is we start to resolve snowdrifts, which means we can deal with late line snow cover and the summer hydrograph, particularly in mountains and the Arctic. But the Vincent Vionnet, I believe, is here. He works for the University of Saskatchewan at the Canadian Meteorological Centre in Montreal, and he's been dynamically downscaling with the GEM model over the Canadian Rockies. And Vincent, correct me if I'm wrong, but the precipitation gets better and better as you go finer. It's down to 250 meters, and it's better than 1 kilometer, and at least in the Canadian Rockies. So that's, now, you can't run it for very long at 250 meters, but it's instructive as to where we might need to go in the future, and maybe at least in complex terrain, we do have to go fine scale, and we just have to say that's where we're headed, and we'll get there somehow.
That's a good comment, John. We see the same thing, and we've even run LES over mountains in Wyoming that you're familiar with, the Laramie Range, and no, not the Laramie Range, the Medicine Bow near Laramie. And what we're finding is that the liquid water, we have a radiometer making measurements. We do not capture the complexity of the radiometer signal until we get down to 100 meters. And a lot of that complexity is due to the interaction of the flow with the terrain, very fine terrain, generating very fine turbulence, and that's impacting your blowing snow as well. So there's a lot to be learned at 100-meter scales. I wish,
The atmospheric and hydrological models are converging in scale.
Yeah, absolutely. Absolutely. At the hill slope. Okay, there you go. Everything's at the hill slope.
Roy, and John, my former student has run the world land surface at 30 meters.
Wow.
And he's coupled it to GFDL's climate model. So there's things happening that are still a little bit under the radar, but he finds interesting biases as you get away from these really fine scales. So. More to,
I hear about this all the time. People run even finer resolution than I am, and I'm just so impressed. I think this is great. I think this is the future, and, you know, you're talking 40 years. We may be down at centimeter scales.
Yeah, so the message from Eric is that it seems that Princeton has better computers than you guys have, so.
They definitely have
hey,
more.
You presented it under
We only have
Princeton,
one.
so I'll take it that was your message. Any other questions? Yes? Are you going to be loud or you need this?
I wonder, what do you think about the estimation of uncertainty that we are driving in the models? We are going to higher resolution, but is it
So,
important to calculate that?
So the question is the estimation of uncertainty. I think that's a very important aspect that we need to take into account. If you saw that diagram I showed you of all the parameterizations, there's many sources of uncertainty. There's model uncertainty. Each of those parameterizations has uncertainty. The observations have uncertainty. All of those need to be taken into account. I'd love to do some ensemble runs, and maybe we're going to try to come up maybe with 10 ensemble members, run it for shorter time periods that capture some of the uncertainty. But it's a very good point. The HEAPEX program is looking at streamflow ensemble simulations. That helps us get at some of the uncertainty. I like to do the same thing with these kind of runs, have multiple ensemble members. It's just a matter, I'm going to ask Eric for some computer time.
Okay, Roy, before you take off, I'll ask one question on a serious note. Is the bottleneck going to be, assuming that, you know, computer cycles are becoming available to allow high-resolution runs, are the mathematical equations to represent the different components already there in order to take advantage of the additional cycles, or there are certain parts of the system that still need better representation? I remember all the work on the cloud resolving models during the GVEX days, and, you know, CSU's super parameterization work. I don't know where they're all converging or not.
I think it's a really great question. If you asked me that question 10 years ago, I'd say, let's put more money in super parameterization. But now, the technology has advanced so rapidly that I think we should put all our eggs in the convective permitting basket and then work in that area. That's what the global weather forecast agencies are doing. The UK Met Office is doing that. Many of the agencies are doing that. I think the climate community is starting to move in that direction, you know, pretty rapidly. A lot of times they do nested simulations over a particular region that they're interested in, but I think it's definitely moving in that direction. Yes?
It's not my area, but I'm curious just about precipitation recycling in this context and how we quantify that. Is it a big number? Is it a small number at the basin scale where we're trying to implement the kind of schemes you're talking about?
It's an interesting question, because if you ask an atmospheric scientist about recycling, it's slightly different than what you ask a hydrologist. So for atmospheric recycling, we're looking at from how far away in the atmosphere does this thunderstorm suck moisture in, or a winter storm. And that's a very interesting question, because it impacts the precip shed. That is a new term that I just saw a seminar last week on. On the terms of the hydrology, I think the coupling of the hydrology and the atmospheric models is really needed to get at the answer to that question. I think that's a whole exciting new area, is running at higher resolution with the coupling. And I'm trying to move my scientists in that direction, and we've done some simulations. We know it's possible. The results look reasonable, but we need to verify.
Okay, Roy, thank you so much. I guess we'll try to wrap up this session. I think Lucia, is that your name? Yes, she actually asked about uncertainties. I think this particular issue is perhaps one of the bigger uncertainties to be addressed. As a simple-minded civil engineer / hydrologist / water resources engineer, you want to say something?
I want to make one more
Go ahead.
last comment about uncertainty. By going to improved physics and high resolution, we are reducing uncertainty.
That's good. So picking up where I started to just wrap up the session, as I was saying, as I'm a simple-minded hydrologist, water resources engineer, the question you always get, and everybody talks about how you communicate with the public, Jay said it, Eric said it, and others. Usually you get the question, you scientists, on the one side you say that the global warming is happening and expected to increase the global precipitation amount. On the other side, you show maps of global stressed areas that are going to get worse and worse. Where are we with this thing? Okay, so this is also one of those big uncertainties. I mean, how could we present a reasonable argument? Where are these extra rainfalls going? That is not necessarily falling in areas where we show that there's a lot of regions that are going to be stressed. So that's $1 million question to address. Thank you so much.